Good afternoon, everyone. The topic of our work is joint compressive sampling and deconvolution in ultrasound, in medical ultrasound imaging. This is the part of my thesis work. So the objective of our work is to reduce the data volume of ultrasound imaging and at the same time to enhance the image quality. So in order to obtain these two objectives, we combine the compressive sampling and the deconvolution. Before going to the detail of our proposed work, I would like to do an introduction about the compressive sampling and deconvolution. So firstly, the compressive sampling. So this is also the title of our session. This is the theory that allows people to recover the original data from a small number of measurements. So the direct model is the equation 1. The y is equal to phi r plus n. The r here represents the original data. So in this case, it represents the ultrasound image data, and phi is a measurement matrix, and the y is the compressive sampling measurements. The n is the additive noise. So we should note that the number of pixels in the y is usually much smaller than the numbers of pixels in the r. So in this way, the image data volume is reduced, and afterwards, the compressive sampling guarantees the recovery of the ultrasound image data from the measurements y under two conditions. The first condition is that the ultrasound imaging data should be sparse in a given basis site, and the second condition is that the measurement matrix phi should be coherent with the basis site. So if these two conditions are satisfied, we can use some classical compressive sampling reconstruction algorithm to recover the ultrasound image data by solving the optimization problem like the equation 2. And there have been some existing work on the application of compressive sampling in ultrasound imaging. For example, for the sparsity study, it has been found that the arc signals are sparse in the Fourier domain. And there are also some work about the incoherent acquisition. This is another example that we can project the ultrasound image data onto the Bernoulli random vectors so that we can get an incoherent acquisition here. So then let's come to the deconvolution. The deconvolution is a technique that allows people to enhance the image quality of the ultrasound image. So the direct model is r is equal to hx plus n. So x here represents the original data, the tissue reflectivity function, and the h is the point spread function here, and the r is the ultrasound imaging data we mentioned just now. So afterwards, the deconvolution technique is to estimate the x from the r. And because this is an ill-posed problem, so usually we need some regularization term. For example, for the linear filtering, we use the L2 norm for the x. So in this case, we suppose that the x is Gaussian distributed. So we use the Gaussian distribution assumption. And there are also some work that assuming the x is Laplacian distribution. So in this way, they employ L1 norm for the x. But we would like to emphasize that it has been recently found the x is more just to the generalized Gaussian distribution. So in this case, the LP norm for the x is employed. Okay, here I would like to do a small summary. So if we have an IF data, the ultrasound imaging, we know that we can use the compressive sampling to do the data volume reduction to get a small number of measurements, because the compressive sampling guarantees the reconstruction of the R from the Y. And on the other hand, we know that the deconvolution can help us to obtain objective image quality enhancement so that we can estimate the tissue reflectivity function X from the R. So we are thinking about if we can build some relationship between the X and the Y, so that we can estimate the X from Y directly, and then we can obtain these two objectives at the same time. The answer is is yes. So we proposed the framework of compressive deconvolution. The model of compressive deconvolution is Y is equal to phi hx plus n. So the tissue reflectivity function X is firstly become the RF data R through the ultrasound imaging system, and then using a sampling matrix phi, we can get a small number of measurements of Y. So afterwards, we need to estimate the X from Y. The most intuitive way to do so is a sequential method. So we firstly use some compressive sampling reconstruction to reconstruct the RF data from the measurement of Y. And then we use the deconvolution technique to estimate the X from R. But we think separate a single problem into two separate steps will give us more estimation errors. So we propose a way to estimate the X from Y directly. So firstly, we give an objective function here. In this objective function, we consider the three terms. The first term is the sparsity for the RF data in a sparse basis psi, and the second term here we employ the LP norm. So in order to generalizing the Gaussian prior, the Laplacian prior, and the generalized Gaussian prior. But here we employ the P, which is between 1 and 2, so that this is a convex function. And the last term is the data attachment. So with this objective function, if we can solve this objective function, we can find the estimation of X. But this is not so easy to be solved because there are three terms and they are very different. The L1 norm, the LP norm, and also the L2 norm. So we find a way based on the ADMM. The ADMM means the alternative direction method of multipliers. So the general objective is to minimize the sum of two functions with two variables. And the constraint represents the relationship between these two variables. With this general objective function, we can write the augmented Lagrangian function as this equation. And afterwards, we can minimize this augmented Lagrangian function respect to different variables iteratively. So this is the iterative solution to this general objective function. The advantage of ADMM is that it can split awkward intersection and objective like this into some relatively easier problems, so we can solve them separately. So back to our problem, there are three terms. They are different. So we find a parameterization way to put our problems into a general framework of the ADMM, so that we can separate these three terms into three subproblems and solve them separately and iteratively. Now come to the results. The first result is based on the simulated ultrasound imaging. So this image is mimicking the kidney. This is the tissue reflectivity function we simulated, and the scatters in this image is generated according to the generalized Gaussian distribution. And we use a simulated PSF to convolve with this tissue reflectivity function, so that we can get simulated ultrasound image data here. And then we take only 20% of the original data and do the reconstruction. We compare our proposed method with different P and the sequential method. The sequential method is to do the CS reconstruction and deconvolution sequentially. So here we employ the PSNR and the SSIM to evaluate our results. We can see that our proposed method is better than the sequential one. The second result is based on the in vivo data. So this is data acquired with a single element US probe on a mouse kidney. And since we don't know the PSF here in practical, so we first use existing method to estimate the PSF and then do the reconstruction. Here we compare our methods with different CS ratio. So we take a different ratio of the original data and do the reconstruction. We compare our method with the sequential method, and we employ the contrast to noise ratio to evaluate the results. We can see that the CNR of our method is better than the sequential one. And we should note that here we employ the P which is equal to 1.5. So finally we come to the conclusion. Our proposed method shows the ability to reconstruct the enhanced ultrasound RF data from the compressed measurements. And the results show that our method is more robust than the sequential method. And also there are some promising results on the in vivo data. And we also show the interest of using LP norm for the X. And our perspectives will include the consideration of the blind deconvolution techniques. So in this case, the PSF should be unknown. And the second one, we would like to consider the case when P is between 0 and 1. And also maybe some techniques for choosing the optimal P. So thank you for your attention. And more details discussion will be welcome for our poster.